All right, welcome back to Professor Wu's lecture series. In today, we're going to continue with previous ideas that we've learned, which today we're going to learn the mathematics of friendship, which links to the idea of spaces, such as row, column space, and null spaces. This will make sense later why how they can be all linked together. But first, we need to understand this concept called a set. A set, in its simplest form, is just a collection of distinct elements. Right? The distinct is the key. Now, for example, here's a set of animals. Right? Notice that they're all distinct. Set of flags, set of integers. Now, with these set, we like to mathematically contain them with these curly brackets. So this kind of tells you it's a set. And in general, we like to denote them, a set, with cursive capital letter. So when it's cursive, so like cursive, these are all ways of represent a set. Now, a set is a collection of distinct elements. It becomes a space. All right. So a space is simply a set, but then you define some kind of property. So for example, here is a set of flags, right? So this on its own, it's like data, right? However, what if you want something to do with the elements inside the set? For example, let's say you want to add up two flags. What does that mean? Well, if it's just a set, then it's nothing is defined. It's just a set. But as soon as you define some kind of property of how elements inside a set interact with each other, then the set becomes a space. So the only difference between a set and a space is that a space defines some kind of property. So for example, if I want to add up these two flags, right? If it's just a set, we don't know how to do that. However, let's say Professor Wu, decide to define something that when you add up the two flags, what's really happening is we're summing the summation of the population of two countries. Right now, it's defined. Now, once this is defined, I essentially created a space, which I called Wu space. Now, there are many, many different kind of space, like Hilbert. That's the one, right? Norm space, right? There are a bunch of different kind of spaces, and depending on the space, we know exactly how the elements inside the set interact with each other because by definition, in this space, that's how things operate. So that's the difference between a set and a space. So another way to define a space is essentially when you define a span, right? So let's say you have this vector, then the span of this vector is essentially every single point along this line, right? Now, what if you have two vectors, this one and this one, right? So therefore, it's all the possible points. So in this particular case, we have infinite possible numbers inside the span, and therefore the set has infinite elements inside the set. And every single element has to be different. Okay. Now, with matrix, then we can define the vectors, right? So over here, if we look at the columns as the basis vectors, then the space spanned by the column is called the column space. So if you look at the columns and you span some kind of space, that is the column space. What if you look at the rows? Then that is called the row space. So notice how column space are in 2D, the row space are in 3D. So the spaces essentially help you define that. Okay, so now that we have an idea of what a space is, we can move on to the game of the day. So how do we find I want to be able to define a friend zone. Well, in the actual class, we will play this quite differently. Let's say we have a couple volunteers. I'll bring a couple people out. We'll call this Melanie, Mel. And then this guy, I'm going to call it Andrew. And I'm going to put Jack here. So 3 people. In this game, what we're going to do is we're going to model Andrew's action as a vector. And Melanie is a system of equations, A. And then Jack is the output. So as Andrew say something or act a certain way, it goes into the system. And with the system, Melanie is going to tell Jack what the output should be. And the output implies whether Melanie has positive feelings, romantic feelings towards Andrew, or is negatively disliking Andrew, or neutral. Okay, so if you take all the elements here, 1, 4, 6, if you add this up, that's your final score. So if the score is positive, that means Melanie is more and more romantically interested in Andrew. If it's negative, it means that it's disliking Andrew, doesn't want to be near him. If it's 0, it means that it's good to be friends with you, but does not feel romantic. Like it feels nothing, basically. She doesn't feel anything romantic towards you. So that's how we can interpret the result. Okay. So for example, so in the game, what we're gonna do is Andrew's gonna do something, and then that will be V1. And then we're gonna record the result. Let's say the result was 0. And then Andrew do something else. V2, 0 again. V3, 0 again. So basically, and then V4, maybe slight positive. And then V5, slight negative. All right. So basically, we're going to have all the positive and the negatives here, and all the possible zeros here. And this forms a space, right? This forms a space. And in this space, essentially, are all the possible actions, that Andrew can do such that it elicits 0 feelings for Melanie, right? So if elicits, and this right here is the definition for us, the friend zone. It's essentially the zone where you elicit 0 romantic feelings. Right. So this is the set of inputs such that the output is 0. Okay. So it will be like this: 0, 0, 0. Everything is just 0. You just elicit nothing out of Melanie. So in the game, essentially, Andrew will do a bunch of things: V1, V2, V3, and then we'll separate them into categories. So this category is, of course, what we call the friend zone. And the friend zone, in the mathematical sense, we call this the null space. Null space. So the idea is really simple. Basically, null space is the set of actions you take that goes into a system and that elicits nothing. You're getting nothing back. Okay, so the game will essentially go like this in class, but you're not watching it. You're watching on the video, so you get the point. Hopefully, so now you understand what a null space is. So if you're in a friend zone, that means the actions you take are mostly in the null space. All right, like try to reconcile those two ideas. Right, you're basically doing lots of null space stuff. So okay, so in mathematics, the friend zone is a set of all possible actions input such that when you take your input and multiply by a matrix, you get a 0 back. Okay, and like I said, we call this null space of A. So if you have matrix A, the null space is the actions that elicits no response, basically. And according to this definition, the friend zone is not a place you get stuck at. You're not getting stuck at friend zone. It's the actions you take that put you in a friend zone. Okay, and it's a set of all possible actions that you take that elicits 0 output. So you can think of this as like basically you are doing it to yourself, essentially. And this idea could be generalized. So A doesn't have to be some like a person, and X is an action. A could be anything you're trying to accomplish, and you're getting not the result you want, which is 0. You're getting nothing back. So a general sense is if you're stuck in the null zone, null space, it means you're just getting no response back. You're getting a 0 for your efforts. Okay, so null space is not a place like in general you want to be at. And so the natural question is, if we have this equation where we have a times x, you get a 0 back. How do you find the null space, which is the solution to this problem? Well, it's actually really easy. Just like everything we've done so far, the null space is solved using Gaussian elimination because we know what the label is. We know what y is, right? Normally we have ax equals to y, and we basically use augment the matrix. But now we know what y is. It's just 0. So when we create augment matrix, all we have to do is set the last column as 0 and solve it with Gaussian. Like you already know how to do Gaussian elimination. The only thing is that you add a label to be 0, and the solution is therefore your null space. Okay, so that's like you can kind of see this, and this system null space has lots of different interpretations. Another interpretation could be, um, let's say you are this matrix, and then this is how they act. This is how they act, X, and then the output is interpreted differently. Instead of like how you feel towards whoever's doing X, the output is interpreted as what X can see about you. So what X sees. So you have a person, they do some kind of X action, and then there's you, and then this is what you show them. Right? Therefore, the null space is the set of actions they do, and you show them nothing. Right? So if you have a big null space, it means that you don't like to show people how you truly feel. Right? This is kind of like a way of thinking that like you are showing nothing. Right? No matter what they do, you're putting up a wall, and this right here can actually be used to model ideas such as vulnerability. Like how big your null space is. If your null space is really big, it means that you're not showing anything, right? Therefore, you're putting up a wall and people cannot get to know you. So the null space is really interesting in terms of relationship dynamics. Over here, we're using it for like to model the idea of a friend zone. Okay, so hopefully you got the point. The null space is the solution, which you get a 0. So let's see if you can do a little practice. What is the friend zone, right? For this matrix A. Okay, so this right here is the matrix, and you're trying to find the null space. And then I want you to answer the question whether these 2 points are inside the null space. Okay, you may remember, how do we find a point is inside a space? Well, we want to know if the point is spanned by the null space. Okay, so pause the video. Hopefully this is nothing really new, and hopefully you can solve this. All right, pause the video. I'm going to move on. Over here is part of the solution. You can pause the video here. Here's another part of the solution. And then over here is yet another part of the solution. Now, with null space, what you could do is, if you have a particular point, you can check if it's actually inside the null space, right? I don't know if you remember how to check if a point is inside a space. Actually, there's an easier way. If you take your vector x, or actually with z here, if you simply multiply by a, you should get a 0. So that's actually a much easier way to check for null space. Right? So here are all the possible solutions you can check. All right. A really quick observation is that the rank, remember the number of leading variables is the rank, right? Is the rank. And the number of free variables is actually the dimension of the null space. So dimension of the null space is equal to the number of free variables. Okay? So the rank plus the dimension. So you can always tell if there is a null space depending on if there are free variables. Now, to find a null space is pretty easy in Python. What we do is we simply put the matrix and then type null space. You need to import it first, and it will give you the vector. And you might see that the null space is different from your null space, but that's okay. Like, because you may have your space defined this way, and they may define it this way, right? It's just from a different perspective, but both defines the exact same space. So a null space, it's okay if the Python version is not the same as your solution. All right, so given this, let's see if you can find a null space again, given these two, okay? So let's say the interaction is different. So Heather, when she sees Josh, this is the space she feels. And when she sees Reed, this is the space, okay? So based on these two matrices, see if you can find a null space for both of them. And then you can say, okay, who is facing the bigger null space? What does that imply? Like, think about what it means if one person has a bigger null space than the other. Okay, then you can think about how Heather feels towards them. So this right here could be uh, uh, um, a way to understand null space. Okay, pause the video, solve this, and I'm going to move on. Okay, so this is the solution. The solution basically says that Josh basically doesn't have a null space. So if you don't have a null space, it means like he doesn't even have a friend zone. Heather's just going to like Josh no matter what he does. Whereas Reed has a big null space, right? So Reed has a giant null space compared to Josh. So Reed has a stiffer hill to climb if Reed wants to elicit some kind of response. Okay. Now, another interesting thing is let's say we have this matrix, right? If we interpret the matrix as stacks of vectors this way, and we got a zero, right? If we multiply by x, we got a zero. That's the definition. What does that mean? It means that x times the first vector is dot product first vector is zero, x dot product second is zero, so on and so forth. This means that x must be orthogonal to every single vector. Right? Remember, when you have orthogonal vectors and you do a dot product, you got zero. So another interpretation of null space is that you're essentially getting nothing when you're projecting x down to v. Okay, so this is interesting, because if we connect this idea to projection, which is we were previously using it as a way to understand like span, right? If we have a concept we don't really understand, therefore we understand the best possible one, which is projection. Therefore, if we have a piece of information and these are your basis vectors, when we perform a projection, we're getting nothing back. This must be a piece of information that you just simply cannot comprehend. You're getting like nothing back. And therefore the set of possible input x can be viewed as set of possible information that could be presented to you. And when it's presented to you, you receive nothing. And therefore x must be something like really difficult to understand or impossible to understand for you, right? So the null space in this particular case are concepts that the space of concepts you cannot comprehend. And therefore, the dimension of the null space can also be interpreted as ignorance. Like, the bigger the null space, right, implies that there are a lot of things you are incapable of comprehending. Therefore, the size is a measurement of your ignorance. The bigger the size, the more ignorant you can kind of see a person is. So now you can insult your fellow friends by calling them a big null space. All right. So, anyways, all right. Now let's relate null space now also to linear dependence. We previously were saying how, like, if you have multiple vectors, they could be dependent on each other. And when they're dependent on each other, this essentially means that you can use any two of them to construct the rest of them, right? So you can use a set of them, and now the two of them can be used to reconstruct this one. And these two can be used to reconstruct this one. That's when there's dependence. Independence means that you cannot use any combination to reconstruct another vector. Okay, so previously we learned how to run the test for independence, which is when you add these up, you get a zero. So the test for independence is the test for null space. They're identical. So you want to merge these two ideas that independence has redundancy. Null space, if there is a null space, right? If null space exists, that means there's a free variable, and free variable implies dependency. However, if your null space are trivial, which means you only get zeros as null space, then we have independence. So this is a null space. Thinking dependence through null space is a connection you want to have. Okay, so now we're ready. We talked about friend zone. We talked about ignorance. We talked about vulnerability. All these things are ideas that could be combined together. And now let's look at how we can use this idea of null space to measure like friendship. And I don't mean friend zone, just like not romantic. Like it could be platonic, right? But it's just any kind of friendship, but more general idea. So let's see if we can measure this. Well, when two people meet, how do we measure if they're going to become friends? Can we somehow quantify that idea? Well, let's say that we have two people, and these two are Valerie and Ursula. Okay, two people. And Valerie, because of her upbringing, she has a set of basis vectors. And Ursula has a different set of basis vectors. Okay, so they're different. Valerie is V, Ursula is U. So they have two different set of basis vectors. Okay, this implies that anything Valerie can say are combinations of these vectors. So x1, for example, is some combination of Valerie's basis vectors, v1, v2, v3, right? This is any thought, anything Valerie could say comes from this space, the span of her vectors. The idea is similar. Anything that Ursula can say comes from combinations of her basis vectors, like u1 and u3. So this is combination of two ideas gives her a particular thought. Okay, so this is anything that Valerie can say, and this is anything that Ursula can say. Now we're going to make an important assumption here, and the assumption says that, well, if everything Valerie says is in the null space of Ursula, that means Ursula will have no clue what Valerie is saying. Okay, that makes sense, but let's just like really confirm that this assumption makes sense. Similarly, if everything that Ursula says, Valerie just doesn't understand anything. I mean, a simple example, right? Ursula maybe speaks Russian, Valerie maybe speaks like Arabic, and there's zero chance they can communicate with each other. Um, um, so I mean that's just language. I guess you can communicate in other way. Anyway, the point is it doesn't matter what Ursula say or do if it's in the null space of Valerie. Valerie would get nothing out of it. Okay, if it's in the null space. Therefore, if that is the case, they're unlikely that they're going to become friends, right? Because they have no way of communicating with each other. In contrast, if everything Valerie says is within the span of Ursula, that means that Ursula is capable of understanding what Valerie says. And this kind of gives the impression that this person gets me and understands what I'm saying, because what I'm saying is within the span of what they are capable of understanding. So if they when you feel like somebody is understands you and gets you, there's a higher chance you're more likely to essentially become friends. So there's the two possible scenario. What they say could be either in your null space or it could be in your span. And whether it's in your span or in your null space, this dictates how you feel towards that person. Because whether this person understands you or not is a big determining factor. Okay. So in mathematically, how do we quantify how much a person gets me? Okay. How do we mathematically quantify that? Okay, let's see. Well, if we want to quantify if somebody understands you, you need to understand that, well, your mind, so this is Valerie, her mind spans some space. Okay, there's some space that it spans. Ursula also spans some space. Well, they're part of Valerie's mind that Ursula do not understand because it's outside of Ursula's span. Similarly, there are parts of Ursula that Valerie cannot understand. However, there's a part of intersection. This intersection implies that they understand each other. So this right here is the space of mutual understanding. The size of this space, the dimension of this space, the bigger it is, the more mutual understanding both parties have of each other. So if we can quantify this space of mutual understanding, then we can essentially figure out how likely they're going to become friends, right? The larger, the better. So how do we quantify this space of mutual understanding? Okay, well, let's go back to our definition of a span, which, remember, span defines a space, a set of all possible points. So any idea from Valerie will come from her span. So combinations of a vector, right? So any thought came from the alpha values Valerie could possibly have. Ursula, similarly, Ursula has this should be you and you. Ursula came from combination of her thoughts. So any possible value came from this combination and this combination. This implies that the point of intersection must be the point where Valerie's and Ursula equal to each other. That means that means they can span the same point, right? And this right here is the key to understand. Mutual understanding is the space of possible points such that two people intersect. Okay. Now we can now write this matrix, right? Remember, this right here we can write it into matrix by pulling the alpha values out. All the alpha values, here are the v's, and here are all the beta values and u's. And we can now simplify. This is just v transpose, and this is u transpose, and this is alpha, this is beta. So the equation reduces down to here. This defines the space where Ursula and Valerie mutually understand each other. The key is we need to know what the vector alpha and beta is. What are the alpha and betas such that they coincide in the same space? And finding this is pretty easy, right? Let's see. Okay. So finding this is easy. So I told you that this is the equation, right? This is the space that coincides with each other. This means that we can move this over here, right? So this now is equal to 0. Well, this right here is a vector. This is a vector. This is a matrix. This is a matrix, and this is a matrix, right? We can now concatenate, and I mean concatenate these two matrices and pull the coefficient out. Notice how when you multiply this down, you get the same thing, right? So this right here is a bigger matrix. You take Valerie's matrix and Ursula's matrix and form a bigger matrix, and we call this F, stand for friendship. So this means that if we simply solve for V, we will know all the possible alpha and beta values that that intersect with each other. And it turns out that to find this, we simply need to find the null space of F. Okay, so this is the null space. And this will, by solving this, it essentially give us the um, intersection between the two friends. All right, let's practice this problem. Let's suppose we have Valerie, Ursula, and John. Right, Valerie, Ursula, John. They all have different spaces. Now, what I want you to do, um, yes. Oh, by the way, so after you find V, right? It has some kind of space. You then look at the rank, the dimension. So if dimension is 2, that's not as much, but you can imagine if dimension is 4, then two people have a much, much bigger space. So the dimension kind of tells you the size, the size of commonality. Okay, so anyways, let's say that um, each row, let's say that we have 3 people. Each row is a single basis vector. And now the friendship score is the dimension of the null space. Okay, so if you find the null space, you figure out the dimension. That is the friendship score. Now, what you want to do is identify the null space between Valerie and Ursula. So why don't you measure how likely they're going to become friends, and then you can do Valerie and John, right? So then you can calculate the friendship score, which is just the dimension of the null space, and then you can then figure out who is more likely to become friends with who. Okay, so that's that. I give you the solution. You want to pause it and then see if you can solve this. And then here's the solution. I think more solution, and that's it for today. So hopefully this makes sense. I will talk to you and see you later.